Intermolecular forces. Let me talk to you a little bit about this. Intermolecular forces can save your lives. Okay. This first slide is explaining to you what's the difference between intermolecular forces and intramolecular forces. It's actually not just a shot of that. This is the title slide. Would help if I connected it. Thank you. Explaining something. Now, I'll actually do a little prep with you guys. I'll show you one or two things. I like to couch this in real stuff. So what's that picture trying to show you? That picture is trying to show you what happens when something like table salt dissolves, right? So this big thing with green and white balls in is supposed to be a piece of table salt that is magnified. Okay, and we've just done bonding. What kind of bonding would you get in table salt?
No, it's not so resistance in the ions.
Look at the electronegativity value. Table salt, what's the formula? What's the compound? Sodium chloride. The sodium's electronegativity value is 0.9. Chloride is 3.0. 3.0 minus 0.9, 2.1. Type of bonding, ionic. So it's an ionic compound. So what you've got here is you've got sodium ions, which are the smaller ones, and you've got chloride ions, which are the bigger ones. And the sodium ions would be positive because they've lost an electron, and the chloride ions would be negative because they've gained an electron. And that positive and negative attraction sticks the whole thing together. Happy? Okay. Now, I did put the PowerPoint in the Teams folder, I think. If you want to look on your laptop, you can get it there. So that's what sticks table salt together, and it's really hard stuff. I mean, if you think about salt crystals, it's really hard little crystals. Okay. Now, what's happening? This table salt's been put into water, and it's being broken apart. Now, why would water break table salt apart? Well, what have I told you about water molecules? They're a little bit polar. Remember? Polar bonding. The hydrogens have got a lower electronegativity than the oxygen. This red and white thing, that red is supposed to be an oxygen atom, and the two white ones are supposed to be hydrogen atoms. And we know that the hydrogen has got a lower electronegativity than oxygen. If you have a look, hydrogen is 2.1, oxygen is 3.5. Subtract those. 4 point, how much? 1.4 or something, which is definitely polar. And the hydrogen is not as electronegative as oxygen. So the oxygen takes most of the electrons. So the water molecule is polar. So the oxygen side of it is a bit negative. That would be attracted to the positive sodium ions. The negative side of the the positive side of the water molecule, the hydrogen side, would be attracted to the chloride ions because they're negative. And what happens is lots of water molecules will gather around one ion and then they just pull it apart. It's kind of like throwing a piece of steak into a pond where there are piranhas. So the ions, nothing happens to them. The water molecules just gather around them and take them off to other parts of the solution. I often, my brain goes on little jaunts when I teach this kind of stuff. I often say to guys, you got a choice. I'm going to throw you into a swimming pool with either a great white shark or a school of piranhas. Probably going to choose the shark. You've got more chance. You know what I mean? If you dodge one mouth, as to try and dodge 200. You've got a chance. And when you throw salt in water, it's the same kind of thing. You throw it in, the water molecule is going to be attracted. All the positive bits of the water molecules will be attracted to the negative ions. The negative bits of the water molecules will be attracted to the positive ions. And as soon as you stir it, the water starts to move. All those ions start to get pulled around, and they pull the ion, they pull it apart. So the ions just go off to different parts of the solution surrounded by water molecules. And now the ions are too small for you to see. So it looks like it disappeared. Still there. But the ions are on their own. Okay, that's what happens when things dissolve. All happy with it? Good. That's what that slide is showing you, or trying to show you. Now, we're going to do this. I'm going to show you a few examples of this. I'll get it set up for Monday. What time is this finished? 20 past. I'm going to get it set up for Monday. And then we're going to go and look at this. We're going to go look at the solubility of these various compounds. And you're going to find that the solubilities are strange. So I'm going to show you now what you're going to see on Monday. All right, I'm going to explain it. I know it's not 100% the right way of doing it, but life's getting busy. So it turns out you take these two compounds. Now, iodine and potassium permanganate, what do they look like? You know. What do they physically look like? Okay, I've actually got a slide here, I think, where I'll show you what they look like. I think that's what I did. There we are. That's iodine and potassium permanganate. I don't even know which is which. I think this is potassium permanganate, and I think this is iodine. And they look very similar. They're both dark purple. They're crystalline solids. They look like quite shiny, and they're solids, right? I think iodine is the one on the left. I think potassium permanganate is the one on the right. Now, if you take those two solids and you put them in different liquids, so you can put iodine and potassium permanganate in water. You could put them in paraffin, or another word for paraffin you could say is hexane, and you could put them in ethanol. See which ones they dissolve in. Okay? And your results, what you find is quite just to see it. You don't seem to be watching now. What you find is this. Now I'm going to just show you. What you find is this. Iodine is almost insoluble in water. But it's potassium permanganate, although it looks the same as iodine, is ridiculously soluble in water. When you put potassium permanganate in water like this, the whole water goes. You put iodine in, hardly changes at all. Hardly at all. Almost not soluble. It's almost insoluble. Tiny bit dissolves, but you can hardly see it. Yeah. Now, if you put them in paraffin, it's the other way around. Put them in paraffin, the iodine turns out to be ridiculously soluble, and the potassium permanganate hardly dissolves at all. Say again?
What is paraffin?
Paraffin, it's an oil. You're gonna find out later on it's carbon hydrogen, just carbon hydrogen compound. And then if you put in ethanol, they're both soluble. So something's going on here. All right. And we've got to find out what it is. And if you understand intermolecular forces, this will make sense. So have you written these down? Okay. Obviously, there's something weird going on here, and we've got to figure out what it is. And that's what I'm going to try and explain. Now, Monday, I'll show you this. We'll actually do the little bit of solubility. If you don't believe me now, I'll convince you on Monday. Water and potassium permanganate both soluble, but in different things. Iodine insoluble in water, potassium permanganate very soluble. Iodine very soluble in hexane, almost insoluble. Potassium permanganate is almost insoluble, and then they're both relatively soluble in ethanol. So let's go and have a look why. All right. So now I'm not going to make you do that task because I'm actually going to teach you this stuff. So this slide here, we're going to come back to it. Okay, we're going to come back to it. So you can leave those. Well, you can put a few of them. You can put a few things in here. You can put the bonding in. What kind of bonding would you expect to exist in iodine? I want you to write the bonding here. What type of bonds in the iodine? What kind of covalent? Pure covalent. Okay. So then iodine is pure covalent bonding. What kind of bonding would you expect in potassium permanganate? KMNO4. Potassium is a metal. Oxygen is a ionic. Yeah. Look at potassium's electronegativity is 0.8. Oxygen's 3.5. Difference is way bigger than 2. Pure covalent.
So what's the pure covalent? Covalent.
Well, pure covalent is the best kind of purest covalent, and then you get polar covalent.
It was 0.
Yeah. So potassium permanganate ionic. Now that's the only thing you can write down at the moment. I've got the solubilities there. We're going to come back to that slide. So let's go and have a look at intermolecular forces first. All right. Now I've given you this slide. This is the one that's got gaps in it. You have to pull them in. Little story for you. Intermolecular forces. A misunderstanding between inter and intra nearly cost me my life. So I went to France. I was teaching in the UK, and my school had a conference. We went to a conference in Paris. I'd never been to Paris before. So I said to my wife, get off work and come with me. So she got off work and we went together to Paris, go and see Paris. So we're staying in a hotel in Paris. And in the basement of the hotel was a tube station. So she stayed in the flat. I go down to the conference, go down the hotel into the tube station, get on the tube, 2 stops, get out. I'm in the hotel where they're having the conference center. Go to the conference in the morning, then we were going to go and sightsee in the afternoon. In the conference for like half an hour, and it's rubbish. So I'm like, forget this, I'm going. Down to the tube station. Now all I've got to do is get on the tube, 2 stops, and I'm back at the hotel for my wife. Stand at the platform, train stops, get on the train. Now I know the station I need to get off. So I'm looking. Station comes, no, it's not this one. No, what's the next one? Station comes, no, it's not this one. Station comes, no, it's not this one. Only 2 stops. Another station comes, no, it's not this one. I better get off. So I get off. I get off it. Get out of the train. Train pulls out. Now I'm at a platform like it. I'm thinking I must go around, get on the other platform, go back to the hotel and start again. But there's no way to get on. You know, you can't jump across the tracks because it's like electric and all that. There's no like place to go over. All there is an exit. There's nothing else. It's like a tiny little station that I've got over. There's no way to get to the other side of the track. Something, oh, maybe you have to go out first and then you can get around. You know what I mean? So I go to the exit to get out. You know, when you go to these sports games and there's these big turnstile gates that like open so that nobody can get in. That's the exit to go out. It's like all barred up. It's like a turnstile gate like this. You push it, click, 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 you go out. You can't get back in. There is no way to get in. So I'm like, I have to go out. I mean, I can't stand on the station. So I go out, walk out. Now I'm outside of this little station. And I'm looking where I am. High-rise block of flats, broken down car, graffiti everywhere, garbage everywhere. I'm like, yes, where have I ended up now? So now I start walking. I'm in a little suit and tie conference stuff. There's like dodgy people everywhere. I've like got a sign on my head, please make me. Now I'm panicking. I can just see I'm in a bad area. I'm in trouble. So I'm walking like this now. I'm trying to walk to the other side of the station, but there's no. So I walk. I see a building, and so I look inside. It looks like a YMCA or something. And I see so I walk in, and there's a bloke in there. Looks fairly decent. I try and speak to him. He can't speak French, so I try and talk to him. He just ignores me and walks off. Like, you need to help me. I'm going to get killed here. So I walk out again. I'm worried. These people checking me out. So I see a busy street. I walk to this busy street and I see another busy street. So I walk to that busy street. It gets busier and busier. I walk, there's a big main street. So I walk and I see 2 cops. But I go up there and say, geez, I tell them what's happened. So they start laughing and tell me, okay, there's a tube station there. Go in that tube station. You should get 3 stops back. And I'm like, okay, fine. So get in the tube station, go back to the hotel, sort myself out, get organized. The next day we leave Paris. Bus comes to pick us up to take us, and we get on. The guy says, right, they're going to give us a little tour of Paris on the way out. So we're on the bus, and there's a conductor guy, and he's telling us about the city and everything. And he says, right now we're driving to. He says, right now we're in the northern suburbs of Paris. He says we're in one of the roughest areas in Paris. He says, if you walk this, he says, if you walk around here, you're going to get mad. As he says that, I see the tube station that I caught the train there. What happened? What are tubes? Tubes are intra-city trains. They're trains which take you in the city. What did I get on? Intercity. I got on a train that was taking me to the next city. I got an intra-city train at the same station. I didn't realize. Nearly cost me my eye. What's the difference between intermolecular bonds and intramolecular bonds? Big difference. The bonds in the molecule are called intramolecular bonds. They're bonds inside the molecule. The bonds in between two molecules are called intermolecular bonds. Now, we should have mentioned to you last year, you might have forgotten. You can never forget that ever again, because these are a massive part of the syllabus. And if you get it wrong, if we ask you for intermolecular bond and you name an intramolecular bond, even if you name it correctly, we're going to mark it wrong. So, so here we go. The two different types of bonds occur. And some of them are intramolecular and some of them are intermolecular. Now, if you're working on the PowerPoint online, the idea is that you take these arrows and you move them to the right place. If you're just drawing it on your thing,
you can't.
No. Yeah, you should be able to. Download it, sure. You must download it. Now, if you're drawing it, just draw them in the right place. So the intramolecular bonds are these in the molecule. The intermolecular bonds are the bonds between two molecules. And I haven't taught you about them before, and now we go start learning about them. All right. But firstly, you must understand the difference between the two different types of bonds.
So those two different water
molecules
bonded. Yes.
There are bonds between them. We haven't discussed them before. Now we're going to.
Intermolecular, but two
different molecules are attracted to each other. Okay. So these bonds here that we've already spoken about. When I've spoken to you about bonding up until now, we were talking about these kind of bonds. What are the bonds in the water molecule? Intra. What types of bonds are there? What is the bond there between that hydrogen and that oxygen? What is that bond? What kind of covalent? Polar covalent, 100%. Okay. Now, the intramolecular bonds, you've only got about three. You've got covalent, polar covalent, pure covalent, or ionic, or metallic. Those are the only types of bonds you've got in the molecules. And 90% of the time, in the molecules we're talking about, they're going to just be covalent. Either pure covalent or polar. Because we're very seldom going to work with the ionic stuff. Because molecules are only formed by covalent bonds. But the bonds between the molecules, I haven't told you about any of them yet. They're brand new. Okay. So now I must go and teach you about those. Happy? Two or more. They don't have to be different. They can be the same. It's molecules.
Two different types of bonds occur in substance.
Yeah, two different types of molecules occur in the substances. Yeah, so is it talking about intramolecular or intermolecular? Inter. So it's between two or more, you could say different molecules, but they can be the same molecule, the same type, but it's got to be two or more molecules. What time do we finish? Sorry? 20 past, so we still got time. Good. You have time?
So,
yeah.
So the test you got vectors, energy, and this, and bonding. Are those all related?
Yeah.
So all like, if you have knowledge on one, you
vectors. Yeah, well, vectors is kind of related. Yeah. Yeah. The energy we're still going to get to. So let's go and have a look at the first type of intermolecular bonding. Now, just let's look at these quickly. Right? Hydrides of hydride boiling point. So what are these hydrides? Look at these compounds here on the left. We've got carbon, silicon, germanium, and tin. Tin is Sn. Where did I find those? Carbon, silicon, germanium, tin. They're elements in the fourth period. Now look at these ones. Nitrogen, phosphorus, arsenic, antimony. Nitrogen, phosphorus, argon, arsenic, antimony. They in the fifth period, fifth group. And these ones are group 6. Oxygen, sulfur, selenium, tellurium. And this is group 7. Chlorine, carbon, chlorine, bromine. So all I've done is I've taken these compounds here, these 1, 2, 3, 4 groups, and we're looking at their hydrides when they bond with hydrogen, which they all do. And we're looking at their boiling points of those compounds. Okay? You're looking at the boiling point. So now, look at the trend. Minus 161, minus 118, minus 100. What's happening as you go down to the boiling point? Minus 161, minus 111. It's getting higher. The boiling point is increasing. What's he thinking? So you agree the boiling point is increasing as you go down. Now look at this one. So as you're going up, the boiling point is decreasing. Right? Now there's a reason for that, and the reason is basically because the molecules are getting smaller. But we'll talk about that still. Look at this one. As you go up, what's happening? So here it's getting more negative, which means it's decreasing. Here it's getting more negative. So it is decreasing. Here it's getting more negative. So it is decreasing. So if I asked you to predict this one, what would you predict? I mean, look, this one becomes more negative, minus 11, 1111 to minus 161. Write a value in there. Just put it in pencil. Just pencil in a value. Make one up. But look at the trend and think what you think it would be. What? I can't just do it in pencil. Try and predict a value for each of those ones at the top. You can see the trend in the group. You're an informed scientist.
Is we mathematically correct?
No, just have a guess. We're just guessing. Do it in pencil so you can rub it out. Because I can tell you now, you're going to be wrong. You know, there's no way you're going to predict it spot on. Right? Somebody give me a value that they chose for ammonia here. Minus 105.4. Okay? Minus 50. Why did you go? No, for this one. Minus 90? Minus 97, okay?
That's 79.
All right. And for this one? Minus 107. Minus 110. Something minus a bigger than minus then. Okay, good. What about this one? What about this one? Minus 97. Okay. Now, let me tell you how this. Let me just tell you how this works. Let's say you're a researcher at university. I don't know if any of you can do chemistry, but let's say one or two of you decide you can do chemistry at Bosch. You can be a chemical engineer, going to have lots of money. Or you're going to go and solve COVID and make a. So now your task for your practical for the afternoon is you have to measure the boiling points of these hydrides. So you measure this one. Then you measure this one. And it's a long, complicated procedure. Then you go and you measure this one. Now you're still going to measure this one and this one and this one. And your mate says to you, hey, listen, there's really good waves today. Let's forget about it. We know what the trend is. Just chip over it. Just chip over it. Just make up the, you know what the number is going to be more or less. Just make it up. So what do you do? Lots of people do chip over their results. Lots of people do. So they chip over it. And you make up those numbers and you scribble them down and you're thinking, let's go. We're off to the pub or we're off to surf or we're off to wherever we're going to go to. If you put them in a graph, that's your graph. up until that point. Where are you going to draw the others? I'm going to go there. There's the trend. I know what's going to happen. It's going to go there. Where's the trend? Silicon, germanium. I'm going to go there. You hand it in and you go and draw for the weekend. The nerds, the guys who like too scared to jippo, they stay and they work them out. Then on Monday you find you've been kicked out of the Boston. Why? Because those are the actual value.
It's H2O, man.
Now, one or two people said to me, hang on a minute, isn't this water? How can you say it's got a minus? Water's boiling point is 100. And if you, so you can write those down now. If you put those on a graph, the graph does this. That's what the graph does. So write those values down. Now listen, guys, if you cheat at university and get away with it, you'll carry on cheating. And if they don't catch you by the time you get qualified, you're going to cheat when you get into your job. And if you get away with it once, you'll do it again. But eventually, you will get caught. The longer it takes to catch you, the worse the consequences will be. The best thing that can happen to you is first you decide never to cheat, or the first time you cheat, you get caught, and you learn your lesson. So these are called, I'll just stop it here. Those are called the anomalous boiling points. They don't follow the trend. This one does. This one follows the trend perfectly. No, just these. Those three are anomalous. They don't follow the trend, and we need to understand why. Thank you, guys. Enjoy your weekend.